Welcome to Ask and Learn.
All right, so here we are given that some value C is greater than D, which is greater than 0. And we are to prove that n to the power of D is big O of n to the power of C, and that n to the power of C is not big O n to the power of D. Okay, so we really have two parts to this, right? So we'll start by proving that n to the power of D is big O n to the power of C. Okay, so we'll let function f of n be equal to n to the power of D then, and our g of n will equal n to the power of C. All right, then we'll just let k equal 1 and take n greater than k. Then we obtain, just by taking the absolute value of f, right? So if we want the absolute value of f, then we're getting the absolute value of n to the power of D. Right, but so n is at least 1 or larger, so it's positive. Okay, so that's just going to be equal to n to the power of D, which of course is equal to 1 times n to the power of D. All right, so since C is greater than D, we know that C minus D is greater than 0. We also know that since n is greater than 1, which we set by choosing k equal 1, then n to the power of C minus D must also be greater than 1. Okay, so that means our 1 times n to the power of D must be less than n to the power of D times n to the power of C minus D, right? Because we know that this is greater than 1, so we have a 1 here. We have something that's greater than 1 over here. All right, but this pair, n to the power of D times n to the power of C minus D, is actually just equal to n to the power of C, right? And since n is positive, this is equal to the absolute value of n to the C. Right, so if we take our big C, which is a little confusing, so we have another C, but this will be a capital C for that constant that's in our big O notation. And capital C equal to 1. Then we get that f of n equals n to the D is big O of n to the C. Right, because we had the absolute value of n to the D here, which is, we got a new color. N to the D is less than n to the C. So that is our definition of big O. Now we have the second part to this, right, where we switch the functions. So instead, we'll have f of n equal n to the power of C, and our g of n will be n to the power of D. So in this case, we're going to assume that f is big O of g, right? So we are essentially assuming that absolute value of n to the power of c must be less than or equal to some constant c times the absolute value of n to the power of d, whenever n is greater than some k. We can choose k to be positive without loss of generality, because if the above statement were true for negative k, it will also be true for any positive k. Okay, so we'll just assume k is positive. So then, since k is greater than 0, we can obtain that n is greater than 0. And if that's the case, then the absolute value of n to the power c is simply equal to n to the power c. And the same goes for our n to the power of d, right? So we get n to the power of c is less than or equal to c times n to the power of d. Oops, I want to get rid of those absolute values. I'm just getting into a habit here. Okay. Well, we can divide both sides then, right? So this is necessarily the same thing as n to the c over n to the power of d being less than or equal to c. Okay, and since c is greater than d, c minus d is positive, which is what that is going to end up being. Right, so this is a positive number. That means it's unbounded. It's an unbounded positive number. So how can an unbounded positive number be bounded by some constant? Well, it can't, right? So this is where our contradiction comes in. I wish contradiction was a shorter word. Okay, and so since we have a contradiction, then we can infer that n to the c is not big O of n to the d.